Okay, so we're going to do an intro lecture into work, and there's about 8 slides here that I want to talk about, and then there was a couple extra ideas about a parallel component and types of work that I also want to go over. So let's get to it. Work is equal to a change in energy, and the symbol for work in this class is capital W, which looks a little bit like weight. So you have to understand context. And sometimes it is work when you see a capital W, and sometimes it's weight. Capital W is also watts. If you think about a light bulb, a 100-watt bulb or something along those lines, or 60-watt bulb. So you would see a capital W for watts as well. So once again, you have to understand context. Are you looking at a light bulb? Are you dealing with energy? Are you talking about a force? And it's going to change for each one. All right, so work is equal to a change in energy. That'll be our first formula here. So we can say that work is equal to, we can say work is equal to delta E. And I will come back to that formula later on in this lecture. All right, the next formula, we can see that work is what happens when you multiply two vectors. So if you take a force, which is a vector, and multiply it by a distance in a direction, which is technically a displacement, but we're going to use d for distance. And both of these are vectors. When we multiply two vectors, we get something called the dot product, and that is also work. And then the final one would be FD cosine theta. All right, so there's our three formulas for work. They're all important, and so it's kind of a complicated idea, this idea of work in physics. But at its simplest, and this is something you don't want to forget, right? Because it's going to seem like it might get confusing, right? Let me see. And if it does, just remember that work is equal to a change in energy, right? And I guess we should say that the symbol E is, or capital E, is energy. So I forget we haven't really talked about energy yet. Okay, and obviously the triangle there is delta. Or maybe not, obviously. Okay, I think that's about it. The only other thing is these vector symbols over F and D. The arrows are just saying that F and D are vectors. Vectors have magnitude and direction. Okay, let's go to the next slide here, which I believe is this one. I'm not sure the order here, but that's okay. I think it goes like this. Okay, so a vector dot product. So this is multiplying two vectors, and it's not as simple as multiplying two numbers. So this is different than just multiplying two numbers, right? If vector multiplication was that easy, there wouldn't be two ways to do it. And there's actually two methods to it that give you totally different answers. So one of these methods is called the vector dot product, which is what we showed, or what I showed a second ago by writing the formula to look like this. W equals F dot D. Okay. This is where you multiply two vectors to get a scalar. So what I'm saying here is both F and D are obviously vectors because they have the hats over them, but work is a scalar, which means it has a magnitude, but doesn't point. Let's write that down. Has magnitude, but does not point in three-dimensional space. And this is tricky, right? Because we're gonna see sometimes that work can be positive or negative. That that our answer here is if it's positive, the system gained energy. And if it's negative, the system lost energy. So and the system is just anything you're studying, right? We're going to talk about that in a second, but so when you see work being negative, don't think that it's direction, right? Because it's not direction. It is just saying that the energy is being lost by something, by the system, and because work doesn't point, right? You would never say there is a 50 joule amount of energy east. It doesn't quite work that way, right? I think you might have talked about energy in biology or chemistry when you talked about calories or you talked about ATP. And so energy is important in physics as well. We like to use joules actually as our unit of energy, but it's a concept that cuts across all the subjects in science, and it is important. So so this idea of work being a change in energy is important too. Okay, so coming back up here to the slide, just making sure I got everything. There's no such thing as negative energy, and energy doesn't have a direction. All right, that's important. So so when you see work being negative, once again, the energy is not negative, right? Because it'll say like negative 100 joules, right? And you're like, oh, negative energy. No, we're just saying that something lost energy. And that's what I have here. This represents energy lost or gained. Okay, so I think we're good there. All right, let's move on. And I guess one more thing, if you're wondering why I would say there's two ways to multiply vectors, this was called the vector dot product. There's another way in physics that we like to talk about, which is the cross product. And an example of the cross product is with torque, where we say torque is equal to R cross F. And here we're multiplying two vectors to get a vector. And so that's why it's different. This is we're dealing with the dot product down here. When you take two vectors and multiply them and you get a scalar, this is called the dot product. And the other one is called the vector product or the cross product. And that's when you multiply two vectors. Whoops, I'm trying to talk and write at the same time. Multiply two vectors and get a vector. So torque is a vector. And what the heck is torque? Torque is turning force. And I know I've talked about that in some of the classes, and if I haven't talked about it enough, ask me about it in class and I'll talk about it again. All right, let's go to the next slide here. A system, the way we can define a system is the object or collection of objects under study. So it's whatever we're interested in, right? And the idea behind it is that things are going to be in the system or out of the system. And I guess before I even mention that, it's important to understand that it's not a physical thing. That the system is an analytical tool, meaning it is it doesn't change anything. So it is something that helps us understand the problem. And so, yeah, let me write that down. A system helps us solve the problem. How we define it changes how we solve it. But it does not change the problem. So meaning, and we'll see this in the future here, that we can take a problem and define the system different ways, and it won't change what happens in the problem, but it will change how we solve the problem and interpret the problem. But if I was to say drop a book on the floor and I was looking at energy for how that happened, the book wouldn't care how I define the system, right? The book would just fall and hit the floor, and it wouldn't care how I solve the problem or define the system. Okay, well, systems are important because if something is outside of the system, we call it external. And if something's inside the system, we call it internal. And furthermore, right, external forces accomplish work, and internal forces do not accomplish work. And so how you define the system defines how much work is being done and the types of energy we have. So let me say that one more time, that how we define the system determines the types of energy present and if work is done. And if you're not quite understanding this, that's okay. That's probably the best thing I can say right now is this is this is an introduction, first of all, and some of these statements that I'm making will make more sense the further we use them and we dig into this chapter. So this is almost like a good lecture to watch at the beginning and a good lecture to maybe come back at a later time and watch, because you might have forgot some of these large ideas. Okay, so why this matters about how large we define the system is because if we make the system large enough, right? If the system is the universe, then and no work is done inside of a system, right? All internal forces accomplish zero work. So if the system is infinitely large, then there's no work being done, then there's no change in energy. Then energy is always conserved. And you should know that from science class, or have heard that before in a science class, that energy is conserved in the universe. This is a law of the universe, right? This is that's how important this is, that energy is conserved. You might have heard it stated maybe in another class as energy cannot be created or destroyed. It can only change forms. And so that's what we're dealing with here. Now, when the system is small, then you lose energy, right? It goes away, right? It leaves the system. But if the system's defined as being the universe and infinitely large, then you don't lose energy, right? It all stays in the system. But it does change forms. And when I say it changes forms, it also changes usefulness. So meaning sometimes it goes to a form that you can't get isn't usable for you anymore. It's there, but it might be given off in a form that you can't easily get back. So energy's form, or the form of energy, determines its usefulness. And we'll come back to that. But I guess I can write it down. Energy has different levels of usefulness. Has, I don't really like the way I'm saying that, but different levels, different, yeah, okay, I'll just go with it. And once again, I think that'll make more sense the more we talk about this. Okay. So calculating the dot product. All right. So coming down here, let's dive into this dot product a little bit more, because we said that multiplying vectors is different based on if it's the dot product or cross product, but we never really said why, right? I mean, I wrote it different. One way I wrote a dot, and the other way I wrote an X, but I didn't really say why. So I'm going to write it out one more time. W equals F with the vector hat over it, dot D. And what this is saying is that if you take two vectors and put them tail to tail, let's go ahead and draw this. I think this is an important idea here. So the vectors must be drawn tail to tail. That theta is the angle between. So right here, this angle, oh boy, let me make that highlighter a little smaller. That angle right there in green is theta. All right. Okay. So when we multiply the vectors, what happens is the formula changes. That the formula we actually use, and the one we'll use the most in this class, is going to look like this. W equals FD cosine theta. And what am I saying with this, right? What I'm trying to say is that a couple things. When you use this formula, I'm going to write it one more time. It's that important. I got rid of the vector hats for one. And I want to point some things out here. That we're interested in the magnitude, which means just the amount, no sign, right? Of these two things, of F and D. So when you use this formula, you will never put a sign on force, right? Like, I don't care if the force is pointed left or down or whatever. Do not put a sign on force. The same with distance. I don't care if it's pointed left or down. Do not put a sign on it. So we only use the magnitudes for F and for D. So you might say, well, a second ago you said work was negative. Where does the negative sign come from? It comes from the cosine of theta. So the angle, right? The angle, the cosine of the angle, right, determines the sign. So I'll just write it that way, right? The cosine of theta determines the sign. So whether it's positive or negative or zero. Whoops. All right. So that's really key to knowing how to use this formula. All right. I'm going to add on to that a little bit. Let me add a page. Whoops. Hold on. Okay. So what we're saying, if I think I added the page in the right place. All right, good. Let's look at an example here. So if we take F, let's put it like, let me think about this. Let's put F like this. And we'll take D and put D like this. And obviously, theta would be this angle right here. So what I want to point out here is that the force F can be split into an F of X and an F of Y. And this creates a 90-degree right angle right here, where theta is still this green angle. And you can see that F would be the hypotenuse, that F of Y would be the opposite, and F of X would be the adjacent. And what I'm trying to say is, what is the adjacent? What is F of X equal to, right? So if I want to know what F of X is, which is the adjacent, I would have to use my cosine formula. So I can go ahead and write that out right here underneath it. I can write the cosine of theta is equal to the adjacent over the hypotenuse. And I can write the cosine of theta is equal to F of X over F, because the hypotenuse is F. And you can see if I write one more line here, I can say that F of X, I can solve for it just by multiplying both sides by F, right? I can solve for F of X and say it's equal to F cos theta. So what I'm trying to say here is that when we find work, if I go back and rewrite the formula I just told you, I think it looked like this, right? And if I rearrange it slightly, when we talk about work, right? F of X is F cosine theta. When we talk about the work being done, work is done by the force component work is done, I shouldn't even say by the force component. It's done when the force and the distance are parallel to each other. So, and the sign for parallel is like that, right? Like railroad tracks. So when they line up, when the force and the distance are parallel, that's when work is done. So if I go back now and look at what we just said, right? That right here, if you look at this, right? And you want to know how much work is being done by this force over this distance, right? How much change in energy is being done by this force, which causes the object to accelerate up and right over this distance pointed to the right. We see that it's only getting done by f of x, right? Which I'm highlighting right now, because that is parallel to d, right? F of x and d both point the same way, right? So what I'm saying is you have, right, you have f of x pointed like this, and you have d pointed like this. And that's when work happens. And you don't even have to worry about the angle if you know those two values, right? So our formula that uses an angle and uses cosine, what it's trying to do is get at the component of the force that is parallel to the distance. That's what you're trying to do. So that formula is helping you find the parallel component, this formula right here. And so that's what you want to realize. And so what I wrote here is only the parallel components of F and D accomplish work. And that's what we're trying to do. Okay. Hopefully that's making sense. I know that that's kind of difficult. And yeah. All right. Before I want to move down here, it looks like I gave myself some room for the parallel component already and I didn't use it. That's all right. Types of work. We said there are 3 types. We said there's positive work. We said there's negative work. And we said there's, I want to see, trying to remember. Actually, I'm going to write these all next to each other because I think you'll like it better when you can see them side by side. And I'll just try and write a little smaller. So positive, negative, and 0. All right. And hopefully that you can see these, because I know the video sometimes cuts off the side of the screen a little bit. All right, positive work. I'm trying to think of the best way to say this. So positive work tends to speed objects up. Tends to. Doesn't always, but tends to. An example of positive work is when you have, let's see here, is when you have the force and the distance parallel to one another, right? And here, this would be actually an example of max positive work right here. Yeah, okay. I'm just making sure I have enough room here. Meaning, we were doing positive work in the last example, but it wasn't at a maximum. This is max positive work. What's the angle here between F and D? Notice I drew them tail to tail. The angle, which there isn't any, right? You might say, oh, there's a little bit of an angle there between the red and the blue line. Okay, well, I would have drew them right on top of each other, but it's hard to see. So I drew them like that. So the angle here is 0. And if you think about it then, when you're doing a max positive work example, you have W equals FD cosine theta, and what is the cosine of 0? And you'd be right if you said 1. And so the formula then simplifies into W equals FD times 1, or W equals FD. And so this is nice, right? That when this happens, when you're doing a max positive work example, when F and D are parallel to each other and point in the same direction, this is what happens. Okay. A negative work situation. Negative work tends to slow objects down. All right. Well, in this case, we have, I think we went red with the force. The distance maybe is still forward. So I'm going to draw a dot. I'll start with a dot again. Maybe the object is still moving forward. But now the force is in the other direction. I think I used blue for distance. Whoops. Try and keep it consistent. And this is when that force tends to slow the object down. I'm trying to think of an example of this. I guess if you were bench pressing in the gym, right? And you had you just took the bar off the rack, right? And you were lowering it down. When you lower it down, the distance is towards you, right? And you're bench pressing, but the force is which way? Right? You don't just drop the bar on yourself, right? That'd be dumb, and you could hurt yourself. But no, you're pushing up, right? When you lower that bar, and you're slowing the bar down so you don't get crushed by the bar. All right, so that would be an example of negative work, and it's tending to slow the object down. All right, look at the angle here. What is this angle right here? And you should say 180. All right, notice I drew them tail to tail still, F and D. Let's write the formula. W equals FD cosine theta. I'll just write it out, then modify it. W equals FD cosine of 180. What is the cos of 180? It is -1. And if you don't have that memorized, that's one you want to memorize. So we get W equals negative FD. And so this is an example of max negative work. Whoops. My V looks like a U there. Max negative work. An example, I keep saying max negative work. What would be like partial negative work or partial positive work? That might be something like partial positive work, or positive work that's just not a maximum might be when you see something like this, right? F and D And sorry, I forgot to label these. And now there's an angle theta, right, that we have to take the cosine of, which is going to mean less work is being done. So this would be positive work, but it's just it's not a maximum, right? Because the two, force and distance, aren't parallel. And in here we see they're parallel, but they point in opposite directions. So this is max negative work. What would be an instance of negative work that isn't a maximum? Well, if the distance was pointed forward, say, still, and let me draw that dot there. And now the force is maybe like this. So meaning only a piece of this force, right, is slowing the object down. That's kind of what we're saying. That only a piece of F that is pointed up and left, only the leftward part of it, right, which points like that, is going to slow the object down, not all of it. And that's kind of why this would be partial negative work, right? Okay. And then finally, zero work. And I wonder if you can guess which way zero work is going to point. You could think of it this way. The cosine of what angle is 0? And it's 90, right? So let's check that out. So let's keep the distance pointed to the right. We've done that with all the problems. Let's have the force pointed vertically. And let's put theta right here. And so we end up getting something like this. Let's write the formula out because it's good for us. Whoops. Cosine of 90 is 0. And 0 times F times D is still 0. And so this is a zero work situation. Now, that might not make sense to you. This is an example of zero work would be you carrying your book bag just in your hands or in your arms, right? Carrying your book bag and walking down the hall at a constant speed. And if you did this, I would say that's zero work. And let's say your book bag was really heavy and you started sweating. And I'd still be like, that's still zero work. And because what we're talking about is not the chemical energy that is being used in your body, right? Because obviously there's some change in energy or work in your body, the ATP being, used up to walk around with your book bag. But I'm saying that the object is not changing its energy. The book bag is not changing its energy, right? Because we're talking about the book bag here when we talk about the object, right? This is the book bag right here, this dot I just drew. And if you walk at a constant speed, then what type of energy is changing? The moving energy isn't changing because your velocity isn't changing. You're not accelerating. The height energy isn't changing because the book bag's height isn't changing. So, and there's no springs involved, so there's no spring energy. And so this is a zero work situation. So work is a change in energy. And if you ever encounter a situation where you think it might be zero work and you're not sure, ask yourself what type of energy is changing. Moving energy, potential energy, of height energy, that's the same thing. Spring energy. And if the answer is no to all those, then you're in a zero work situation. All right, so there you have it. 3 types of work. Oh, we didn't draw it. Oh, we did draw it. I just drew it. Okay, I see. I didn't draw a partial zero work situation. That's what I was thinking. All right. Yeah, obviously not. All right, cool. Hopefully you can see all that. I don't think you can because, like I said, the screen kind of cuts some of this off. And so that is what we're talking about.